This is a review of what we covered in class on covalent bonding. So let's start by comparing ionic compounds, which we learned about in our last chapter, to covalent compounds that we'll be learning about in this chapter. First, ionic compounds always consisted of a metal and a nonmetal. This is because there was a transfer of electrons from the metal, which became a cation, to the nonmetal or anion. For example, in sodium chloride, we would see sodium giving an electron to chlorine, and the static attraction between that forms sodium chloride. Sometimes it wasn't a 1-to-1 ratio because we always ended up with a neutral compound. So, for example, calcium chloride, calcium would lose 2 electrons, but since each chlorine could only pick up 1, we ended up with calcium chloride, CaCl2. Also, we might see a metal with a polyatomic ion. These were groups of covalently bonded elements that behaved as a single unit, like calcium hydroxide. So these would be some examples of ionic compounds. In covalent compounds, what we see are 2 or more nonmetals involved in the bond. And instead of transferring electrons, they share electrons with each other. In fact, we'll be learning to draw these into these structural formulas showing exactly how they're arranged in space. So, for example, water is a covalent compound, or glucose that you may have learned about in cell respiration, or phosphorus pentachloride. All of these would be good examples of covalent compounds consisting of 2 or more nonmetals and the sharing of electrons. Another thing that we see here is that all ionic compounds were solids at room temperature, but covalent compounds are actually solids, liquids, or gases at room temperature. For example, water is a liquid, glucose is a solid, and carbon dioxide is a gas. Next, ionic compounds had very high melting points, over 1,000 degrees. Covalent compounds tend to have lower melting points. Ionic compounds also conduct electricity. Covalent compounds sometimes conduct electricity. And there's a major difference here between a formula unit, which is what we call the lowest whole number ratio in a crystalline solid of an ionic compound, and a molecule, which is the actual ratio of atoms in a covalent compound. For example, sodium chloride really exists as sodium and chlorine and sodium and chlorine in this three-dimensional crystalline structure. We write sodium chloride as NaCl because that's the lowest ratio. In a covalent compound, like peroxide for example, peroxide has the formula H2O2. We don't reduce that to HO because in reality, peroxide literally has 2 oxygens bonded with 2 hydrogens. We also see the same thing in glucose, C6H12O6. We don't reduce that to CH2O because a molecule of glucose literally consists of 6 carbons, 12 hydrogens, and 6 oxygens in a 3-dimensional structure. We can draw covalent compounds in a lot of ways, but usually what we draw is the Lewis structure, which shows our bonds or our shared pairs of electrons as a line. We can have single bonds, double bonds, or even triple bonds representing 1, 2, or 3 pairs of electrons being shared. I have a separate tutorial on drawing Lewis structures, so I don't want to spend too much time with it here. But the simplest thing to do is take your compound, add up the total number of valence electrons. You get this from the periodic table. So carbon has 4, and hydrogen has 1, but there's 4 of them, so that's another 4. That means we need to place 8 electrons. Usually you can put the first thing in your formula in the middle. So we're going to put carbon in the middle, and we're going to surround it with our hydrogens, like this. Now we're going to figure out how many electrons we've already put into bonds. So we know that each line, each bond, is a shared pair of electrons. So we have placed 1, 2, 3, 4 bonds, meaning 2, 4, 6, 8 electrons. And so in this particular case, take away 8, we have no electrons left to place. Does our carbon have 8 electrons around it? Yes, it does. 2, 4, 6, 8. And our hydrogens don't want 8, they only want 2, because hydrogen is very unique. Being on the top row of the periodic table, it's already got a full outer shell when it has 2 electrons. In some cases, if we redid this with carbon tetrachloride, for example, we have a lot more electrons to work with. Chlorine has 7 times 4, that's 28, and carbon has 4 more. That makes 32. If we follow our same rules and we connect, make that a chlorine, and we connect our chlorines to our carbon, now what we see is, at this point, we've taken care of 8 electrons. That means we still need to place 24. Now, our carbon already has 8 around it. 2, 4, 6, 8. But our chlorines only have 2 electrons each. So we need to give each of them 8. We're going to see if 24 will cover the amount that we need. 1, 2, 3, 4, 5, 6. That gives that one 8. 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. 19, 20, 21, 22, 23, 24. All 24 electrons have been placed. All of our chlorines have 8 electrons, and our carbon has 8 electrons, so everybody's happy. Our next issue was what to do if we ran out of electrons to place. For example, in nitrogen, there's only 10 electrons. If we connect our nitrogens like this, that takes care of 2. That leaves us with 8. 1, 2, 3, 4, 5, 6, 7, 8. I've placed all the electrons that I have, but the nitrogen on the left does not have 8 around it. So what we can do is we can take a pair of electrons from here and make them a shared pair instead of an unshared pair. If we do that, we now have given this one 6. The one on the right still has 8. If we take away another pair, now each of them have 8. And we only do this if we can't satisfy the octet rule using our first set of rules. Our next rules had to do with those that could be electron deficient, and there were 2. Boron, because of its location on the periodic table, would tend to only form 3 bonds. Notice it only has 6 electrons around it, but that's okay. And beryllium would do the same, but it would only form 2 bonds, and that's okay. If we have too many electrons to place, for example, in these pictures here with sulfur hexafluoride and phosphorus pentachloride, we would still connect everything to the middle. Obviously, this is going to give our sulfur 12 electrons around it, and it gives our phosphorus 10 electrons around it. It doesn't work for everything, but sulfur, phosphorus, iodine, and some others further down the table can do this and have expanded octets. Or here's another example. Let's say we're talking about iodide ion, which is I3 with a negative charge. This has a total of 22 electrons to place. If we start, we have I connected to the other 2, like this. This leaves us with still 18 more electrons to place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And as you can see, the iodine in the center ends up having an expanded octet with those extra electrons around it. For polyatomic ions, remember those were covalent compounds that actually had an overall charge. So there's a drawing there of ammonium, or another one we might see might be sulfate, SO4 with a -2 charge. Sulfur has 6, as does each oxygen. So that would be 30 plus 2 more, 32 electrons. So we start by putting everything here. We take away 8, that's 24 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 22, 23, 24. Everybody's got 8, and we put brackets and show our charge. Alright, a coordinate covalent bond is actually not on the test, but a coordinate covalent bond is when one element donates both of the electrons. For example, if we look at the carbon and the oxygen in carbon monoxide, when we first draw it, we realize that the carbon is going to be short. So what we can do is our oxygen can give a second electron and a carbon can give another electron, and now we end up with our double bond, like this. The problem is, when we get to our next slide, carbon can't give away another electron, oxygen gives both. So in this case, oxygen donates the whole pair of electrons for that third bond, so that we end up with this, and both of the electrons for our third bond came from oxygen. So that's called a coordinate covalent bond. And here's a diagram of what it can be shown as, but again in class, you don't need to know it for our test. Another concept that you do need to understand is resonance. In some of the compounds that we drew, there were 2 or more ways that we could draw them, and this was called resonance. In this case, if you look at the nitrite ion, we see that the double bond can go here on the left or here on the right. There were really 2 ways to draw it. However, the truth is that it doesn't just bounce back and forth between these. In reality, what we know is that the real bond is sort of a mixture of the 2 drawings. And so that's what we call a resonance structure. Here's another example in ozone. We can draw it both ways, representing the possible locations of the double bond. But the fact of the matter is, what's actually happening in ozone is a hybrid of the 2. And here's yet another example, carbonate ion, and we see in this case there's 3 different resonance structures. The next concept we discussed, and we really just touched on it, had to do with bond dissociation energy. Since covalent compounds are held together by these covalent bonds, there's an amount of energy that's required, that's sort of held in that bond, that's required to break the bond. So technically, in another chapter, we could discuss this more. We could talk about how much energy it would take to break a covalent compound down. For example, if we had methane, and we wanted to know how much energy it would take to completely break down the methane into the carbon and the 4 hydrogens. Well, we could look up how much energy it would take in kilojoules per mole to break carbon-hydrogen bond, 1 carbon-hydrogen bond. And here we see it's 413 kilojoules. Since this compound has 4 of those, it would technically take 413 times 4, or 1,652 kilojoules per mole of this compound to break it down completely, because you would have to break in every one of these 4 separate bonds. Another example of this that we did in class was carbon dioxide. If you draw carbon dioxide, it looks like this. So if we wanted to break carbon dioxide down, we know that we would need to break 2 carbon-oxygen bonds. Not just carbon-oxygen bonds, but carbon-oxygen double bonds. And so we would need, over here it says, 745 kilojoules per bond. So 2 times that number would give us the amount to completely break it down. We'd learn a lot more about this in another chapter when we talk about thermodynamics. However, this was sort of a preview just to give you an idea about energy and bonds. Our next concept is Vesper theory, which stands for valence shell electron pair repulsion. All it really says is that the reason that molecules have the particular three-dimensional shapes they have is because electrons, the pairs of electrons, want to be as far apart from one another as possible, like charges repel each other. So for example, our first shape, our three-dimensional shape that we can see, is called linear. So this makes perfect sense. If we have beryllium and it's bonded to two hydrogens, what would be the furthest apart that these electrons can be from each other? 180 degrees. You can't get any further away than that. And so when we have exactly two pairs of electrons, 1, 2, and they're both involved in sharing with something else, we end up with the shape of linear. This is another example of linear in carbon dioxide. It sort of appears like there's actually 4 pairs of electrons being shared. However, there's a special name for the second bond. This is actually called a pi bond. So for right now, just assume that even if it's a double bond or even a triple bond, we're still only going to count that as one shared pair of electrons for the purposes of determining molecular geometry. So in this case, with carbon dioxide, again, we're imagining that there's exactly 2 shared pairs, and the farthest apart that they can be from each other would be 180 degrees. So this is our next possibility. In this case, we have 3 shared pairs of electrons. So in boron trihydride, we see a boron with hydrogen, hydrogen, hydrogen. There's no unshared pairs, literally just 3 pairs, and they're all in bonds. Well, the farthest apart they could possibly get from each other would be 120 degrees. And when you build this, like we did, this would sort of lay flat on a table, and you can imagine this geometrically being 120 degrees, the farthest apart they could get. Another example of this would be in carbonate, CO3 with a -2. When we draw that, we actually get this, carbon, oxygen, oxygen, and our -2 here with all of our dots, of course. This shows resonance. But again, if we were to look at how many pairs of electrons are there? 3. 1, 2, 3. How many of them are unshared? None of them. They're all involved in bonds. Then this also would show this trigonal planar, sort of like a triangle, in the same plane, flat, geometry. Our next 3 shapes all have to do with there being 4 pairs of electrons. So if there are 4 pairs of electrons, you might imagine that it would be 90 degrees between them. I mean, if you draw it two-dimensionally and lay it on a table, you go, well, the farthest apart they could be would be 90 degrees, wouldn't it? And the answer is no. If you actually build this in 3-dimensional space, like we did in class, you can see that we can actually get them farther apart when we include all 3 dimensions. They can actually be 109.5 degrees apart. And that's what we see in methane, and that is called a tetrahedral structure. So 4 pairs of electrons, all of them involved in bonds, and we see a tetrahedral shape. Our next shape involves, again, 4 pairs of electrons, but one of the pairs is called a lone pair because it's not being shared. And this is what we see when you drew ammonia, like this. You had 3 bonds and 1 pair of electrons left over when we drew our Lewis structure. What's going to happen is this pair of electrons right here forces everything away from it. So we end up with not that 120 degrees that we saw in the trigonal planar where they all laid flat on a table, but this literally stands up on a table like a tripod. And the electrons, the lone pair, would be up here. And so this is called trigonal pyramidal, like a pyramid. So 4 pairs of electrons involved around the central atom, but 1 pair of those 4 is not being shared. It's a lone pair. And our next one is called bent. So there's actually a couple of different kinds of bent. You can also have a bent like this, where there's one unshared pair of electrons. But the bent that we're talking about right here is the kind that we get where we have 4 pairs of electrons, just like we did in the tetrahedral, but 2 of them are not shared. In fact, they're showing these purple cones here are actually representing the unshared pairs. Since they force everything away from them, it forces these 2 bonds closer to each other, and we end up with a 104.5 degree angle. And so this is what we see in water. 4 pair of electrons, but 2 pairs are unshared, and this one is called bent. So again, what we're looking at, and we only do this, by the way, around the center. In other words, for each one of these, when I talked about the number of pairs of electrons, I was referring to if we pick an element, the element in the middle, and we're looking at how many pairs of electrons surround that one element. If you were looking at some sort of complex thing, like this, where you have, for example, CH3, let's say OH, in this particular case, what we see is more than one shape. In other words, you'd have to look at each element at a time. This is a central element, and this has 4 pairs of electrons. So this area would show a tetrahedral shape. But we also have, if we count this oxygen as a central atom, it actually has 4 pairs of electrons and 2 are unshared, so it would show a bent shape. So just a heads up that for our class, we're just looking at where there's one atom in the center. But if you were to go on to AP Chemistry, you could be looking at a very complicated molecule, and you could be asked for the shapes of different areas of that molecule. Alright, and as far as what you were required to memorize for the test, it's these. If there's 2 pairs of electrons, and they're all in bonds, that's linear. 3 pairs of electrons and they're all in bonds, that's trigonal planar. 3 pairs, and we didn't really talk about this one, this is the bent with just one unshared pair. This is our 4 pairs of electrons and they're all involved in bonds, 4 pairs of electrons with 3 involved in bonds, and 4 pairs of electrons with 2 involved in bonds. For all of these, you need to know the name of the shape, and you also need to know the bond angles. This one was 109, this one is 107, and this one is 104. So the next section is about polarity, which has nothing to do with being cold. Polarity has to do with a bond having an uneven sharing of electrons. In other words, we sort of acted like at the beginning of this chapter that everything was either ionic or it was covalent, like a black and white sort of thing. It's actually not like that. It's all based on electronegativity. If you recall the periodic table, and electronegativity increases as you go across. Now, if there's a huge difference in electronegativity, we're going to see an ionic bond, where one thing is going to take electrons from the other. And if the electronegativities are super, super, super close to one another, we'll see a purely covalent bond. But what happens if the electronegativities are somewhat different from each other? In other words, where do we draw the line? And what happens in the middle is called polarity, or a polar covalent bond. And that basically means that electrons are still being shared, but they're being shared unevenly. And we represent it with this little Greek letter. It looks almost like an 8. And that represents partial charges. In other words, if fluorine, in this case, is pulling harder on the electrons than hydrogen, then the electrons are sort of hanging around fluorine more, and we end up with a slightly negative charge on that side. It's still sharing with hydrogen, but the electrons, since they're kind of hogged by fluorine, we end up with a slight negative there and a slight positive on the hydrogen. And it turns out that some of the shapes that we've been talking about, some of it's also determined by polarity. And here you see another diagram of it. And again, this delta symbol indicates partial charges. This is another way it can be drawn, with the arrow showing the direction that the electrons are being pulled. So this table is meant to sort of simplify it for you. What you would do if you were asked if a bond was polar or non-polar, covalent, or ionic, is you would look at the periodic table, and look up the electronegativity of each atom. And then figure out the difference between them. In other words, subtract. And figure out what the difference is. So if that number comes out to be from 0 to 0.4, then you're going to say that for the most part, this is a nonpolar covalent bond, meaning the sharing is pretty much even. Between 0.5 and 1.9, we're going to say that it's polar, and 2.0 and up, we're going to say that it's ionic. Again, there's kind of a gray area in here, but for purposes of our class, just use this as your guide. So here's a sample. Let's say I wanted to know if the bond between nitrogen and, let's say, fluorine was polar. Well, fluorine is 4.0 and nitrogen is 3.0. If we subtract, we get an electronegativity difference of 1.0. And going back to the chart, you'll see that that would be a polar covalent bond. Now, just because a bond is polar doesn't mean the whole molecule is polar. For example, the carbon to oxygen bond is polar, but when we draw carbon dioxide like this, we have basically this 180-degree angle, if you recall from our drawing. You have a 180-degree angle, and you have oxygen pulling this way and oxygen pulling this way. It's going to be exactly equal. So the overall molecule would actually be nonpolar, even though this bond and this bond by themselves are considered polar. If we look at water, on the other hand, we had this. So the bond to oxygen is polar, it pulls this way, and this one is polar, and it pulls this way, and we actually end up with a polar molecule with a general pull in this direction. Our last concept has to do with attractions between molecules. For example, we said that CO2 is a molecule. Now, if we look at CO2 and there's a bunch of CO2s floating around in the air, we know that this is a gas. That means there must not be any attractions between one CO2, carbon dioxide, and another carbon dioxide. Because if there were attractions between them, they would sort of stick together and we wouldn't have a gas. Now, on the other hand, water is a liquid. That means that if there's a water molecule and there's another water molecule, we know that there must be something going on, that they're kind of sticking to each other, not reacting, but sticking to each other, and that's why water is a liquid. And we know that in solids, molecules are so attracted to each other that they're sort of stuck in place, just vibrating. So there has to be attractions between molecules. And it turns out there are actually three kinds of attractions between molecules. Not bonds, we're not talking about within a molecule like these bonds in water, but what attracts one water to another water that makes it ice, for example, when it's cold, or makes it a liquid at room temperature. So the first kind of attraction is called dispersion forces, or sometimes called van der Waals forces, or I've also seen it called London dispersion forces. Bottom line is, remember that electrons are always randomly moving. So if you imagine all of us randomly running through the classroom, at any given time, if you took a bunch of pictures, there might be moments during that bunch of snapshots where there were more people on one side than the other. Maybe more people on the right side. And maybe in this split second, there were more people on the left side. And maybe here, there were more people in the middle. And the bottom line is, electrons, being that they're moving randomly, the same thing can happen. That for just one quick moment, you could have more electrons on one side of the nucleus than the other. Now, if there's more electrons over here, that means it's going to be a little bit more negative over here and a little bit more positive over here. And that means that in the molecule next to it, it's going to repel electrons away because negatives and negatives repel each other. And it's going to become a little bit positive here and make it a little bit negative here, and so on. Now, again, this is something that's only because electrons are moving around randomly, and it would only be happening for split seconds at a time. For the most part, it doesn't make a difference. If we were to look at helium floating around, we know that helium has 2 electrons. So yeah, it's possible that for a split second, both of those electrons are on one side, and for another split second, they're on the other side. but it's only 2 electrons, and it's not enough to really make a difference. And so helium is like always a gas. If you want to freeze helium, you have to lower the temperature to like negative 200 something Celsius. But if we look at something like iodine is further down the periodic table, and it has so many electrons that this one factor, just this random motion of electrons, is enough that it makes iodine molecules stick together. And iodine is actually a solid at room temperature, just because of the random motion of electrons, because there are so many electrons. This diagram kind of shows what we're talking about. This picture shows there's 3 electrons, but because they're randomly moving, for this split second, the 3 electrons are on one side. And if there was another molecule close to this one, that would cause this slight negative charge, which would then cause electrons to be repelled to the other side of the nucleus in this atom. And it could continue in sort of a chain reaction. In something like helium, it doesn't make a difference. But in something big like iodine, it could be enough of a difference that it actually causes enough attraction that they actually end up as a solid. The second kind of attraction is called dipole interactions. Now, dipole interactions have to do with not just the random motion of electrons, but when molecules are already polar. In other words, when we look at water, we said that water is an example of a polar molecule. The oxygen is slightly negative, and the hydrogens are slightly positive all the time. So this is not random motion of electrons. That means that when another water molecule is close to it, what's going to happen is this slight negative is going to be attracted to the slight positive of this other hydrogen. And this is going to continue in a chain reaction. We see this in all kinds of polar molecules, and this is a little stronger. In fact, this is a bit more likely to make something a solid or a liquid as opposed to a gas. And the last kind of interaction is called hydrogen bonding, which is a little misleading because it's not really a bond. It's actually just a really, really strong attraction. And it specifically has to do with hydrogen. In fact, the example I just gave of dipole interactions would technically be hydrogen bonding. Hydrogen bonding really is a type of dipole interaction. You have this slight positive on hydrogen, and in this water you have the slight negative on oxygen, and we actually represent hydrogen bonds with a dotted line. You may remember it from DNA, A connecting to T and G connecting to C in a DNA molecule. That was actually hydrogen bonds holding the 2 sides of DNA together. This is the strongest of the intermolecular forces. So to summarize, you have your London dispersion forces. Those are very, very weak, and they are basically just due to random motion of molecules. They don't even make a difference most of the time, but if the molecule is big enough, it can. Next comes dipole interactions, and this is where a polar molecule is attracted to other polar molecules. And then finally, a special kind of dipole interaction, if it specifically involves hydrogen, then we're talking about hydrogen bonding. In addition to ionic and covalent compounds, there's also something called network solids. And I think I told my class this isn't on your test, but just a quick comment. These are solids where the atoms are all covalently bonded into one giant mass. And the best example of this probably would be diamonds. In diamonds, you have carbons bonded to other carbons. And if you recall, carbons can make this tetrahedral shape. And what happens is every carbon is bonded to 4 other carbons, and it becomes such a strong molecule, or basically a network, that it makes it almost unbreakable. And it's got a super high melting point. It's not like a normal covalent bond, because literally it's a bunch of atoms in this gigantic covalent mass. And here's a diagram that really, I think, shows it. Graphite's what's in your pencils. And notice what happens in graphite. You have carbons bonded in rings, and then just this weak attraction between the layers of the rings. And that's basically what's in your pencil. That's why you can write with the pencil lead and it comes off. But notice what happens in a diamond. Diamonds are formed under these really high pressure and temperature circumstances, and you have the carbons all covalently bonded to each other. And so diamond is super strong. Alright, and this is the very last section of the chapter, and it's about how to name covalent compounds. So with ionic compounds, it was sort of a pain, because with ionic compounds, if it was in D block, you had to use Roman numerals, you had polyatomics, there was all kinds of crazy stuff going on. Well, with covalent compounds, this is really simplified. All you're going to do is use prefixes, and the prefixes are going to tell you exactly how many of each thing there are. They are always going to end in "ide," and so it's going to be basically the name of the first thing, prefix, the name of the second thing, and "ide." Now, if there's only one of the first thing, you don't use mono. If there's more than one, then you do need a prefix. So let me give you a couple of examples. Alright, so let's say you were doing this one, PCl5. So we name our first thing, phosphorus. We're going to end it with "ide." So the second thing is chloride. And how many of them are there? 5. So it's phosphorus pentachloride. That's it. Let's say it was P2O5. Now we put a prefix in front of our first one, diphosphorus. And again, there's 5 oxygens, so pentaoxide. I think actually it may just be pentoxide. Alright, let's try another one. Alright, here's a couple more. So this one is going to be carbon. There's only one oxygen, so it's going to be monoxide, carbon monoxide. This one obviously is water, but if we were going to name it using these rules, it would be dihydrogen monoxide. And this third one is ammonia, but again, it would be nitrogen trihydride. And yes, even though it's hydrogen, it still ends in "ide" for the purposes of covalent compounds.